Welcome to The Explainer. I am so thrilled you're here today because honestly, we're embarking on a truly fascinating journey. We are going to explore a groundbreaking mathematical translation. Think of it like a literal Rosetta Stone, but one that translates the physical, messy shape of reality into the invisible, unyielding laws of logic. That's right, we're talking about Cadison duality for partially convex sets.
I want you to just think about that for a second. What if the physical boundaries of the world around us and the pure abstract rules of algebra aren't actually different things? What if they're literally just two different languages telling the exact same story? Well, today, we're going to find that bridge. The bridge between the geometric reality we can actually see and the pure algebra we can't.
Section 1. The shape of reality, mapping boundaries.
Section 2. The classic Cadison bridge, geometric math.
Okay, let's dive right into this. To really appreciate the new discoveries we'll be looking at, we have to rewind a bit and look at the historical evolution of how math bridges shapes and rules. Specifically, we need to look at a massive cornerstone result from 1971, the classic Cadison duality. Basically, this theorem acts as a flawless translator through what we call a canonical bijection. And a bijection just means it's a perfect two-way street. Every single point in an unbroken, perfectly harmonious geometric shape, like a convex set, has exactly one unique mathematical function assigned to it, and vice versa. The geometry of the shape and the behavior of the algebra, they mirror each other completely. If you know one, you absolutely know the other.
Section 3. Enter partial convexity, a messy reality.
But here's the catch. What happens when our shapes aren't perfectly simple? When those old, reliable 1971 mathematical tools just completely break down on us? Take a look at the system mapped out here. Notice how it's bounded by rigid straight lines, right there at y equals plus or minus 1, but it's also bounded by the curve of a hyperbola. This is definitely not a simple convex shape in every direction. It's a system that's only harmonious or convex depending on which variables you hold fixed. If you let it all move at once, it gets incredibly complicated really fast.
And that brings us to the first main character of our narrative, the partially convex set. Notice how we're focusing in on that slice right there. If we lock down the variable y, the resulting slice in the x variable is completely convex. It behaves itself, but only conditionally. It represents this physical, conditionally structured geometric realm. Basically, it's reality, but with strings attached.
Let's draw a really sharp contrast here so we can see the evolution. Classical convexity? That's your simple, unbroken harmony across every single dimension. Easy, right? But partial convexity, it's highly conditional. It's complex. It's essentially a broken bridge. And this proves exactly why the old rules just aren't cutting it for this layered, modern geometry. We need an entirely new mathematical translator for this stuff.
Section 4. The Algebraic Rulebook, Invisible Constitution. So, if partially convex sets are our physical stage, let's bring in the second main character of our story, the invisible constitution that actually governs them, the algebraic rulebook. More specifically, a free order unit module. Now, don't let the dense terminology scare you off here. Without getting completely bogged down in equations, think of a C-star algebra as this underlying mathematical scaffolding. It allows us to measure distance and structure in highly abstract spaces. It's really the heroic hidden code that steps in to solve our problem. If the physical shape is conditional, this algebra steps up and provides the rigid rules that make those conditions actually function.
So how does this rulebook actually play out in practice? Well, first, it evaluates those specific geometric slices we were just talking about using what's called a local order unit. Think of it as a sort of mathematical safety net. It ensures topological regularity, which basically means the math stops the shape from suddenly tearing or jumping or just breaking apart in mathematical space. It holds everything together continuously as a space of partially affine functions, and it dictates the exact shape of the coordinate state space. Ultimately, these are the unyielding, completely invisible laws that conditionally govern the physical shapes we're looking at.
Section 5. A new Cadison duality, the ultimate translator. And this right here brings us to the absolute climax of this explainer. This is where mathematical researcher Tay Streckelage recently made a massive, literal game-changing leap by establishing Theorem 1.5. Just notice how the two columns here perfectly align. The algebraic rules on the left mirror the geometric shapes on the right, flawlessly. Streckelage proved that the free order unit module corresponds exactly to the coordinate state space. And that space of continuous partially affine functions, it maps absolutely perfectly onto a compact, regular partially convex set. It is a pure mirror image bridging two incredibly complex realms. Every single complex algebraic rule has a perfectly matching complex physical shape.
Okay, so what? Why does this actually matter to us? Well, Theorem 1.5 proves that physical shapes and invisible algebraic functions are, at their core, exactly the same thing, just expressed differently. It means that even when reality gets conditional, fragmented, and just plain messy, it is still governed by an absolute, perfectly matching set of underlying rules. Literally nothing is truly random here. It's all just following a much deeper algebraic constitution.
Section 6. The Invisible Constitution. Personas of Arithmetic.
Now, I want to elevate this mathematical proof to its profound existential implications. Let's view this through a philosophical framework known as the personas of arithmetic. There is this incredibly powerful concept from our source material that states, arithmetic is the law, and judgment is the filter that decides which parts of the void are allowed to be real. The void in this context represents endless, unstructured mathematical possibility, just pure, unadulterated chaos. In this view, mathematical limits and boundaries aren't just numbers on a chalkboard, they're literal judgments. They are active, shaping forces filtering out that chaos to dictate what is fundamentally true and what is even allowed to exist in our structured reality.
Let's bring this abstract math directly back to you and the world you actually live in. What we've uncovered today implies that geometric boundaries are literal manifestations of logical judgments, a singular, overarching rule, what the sources refer to as a macroscopic measure, forces structural harmony right onto the universe. Reality itself operates as a giant topological filter, constantly separating what can exist from what absolutely cannot. Our physical world, even with all its messy, partial convexity, perfectly obeys this uncompromising, invisible, transfinite architecture. It's a structure that extends far beyond ordinary limits to continuously, relentlessly dictate reality.
Which ultimately leaves us with this one final thought. If our universe's complex, highly conditional geometry perfectly mirrors an invisible, unyielding algebraic law, who or what wrote the rulebook? It is a deeply provocative question, one that completely blurs the lines between pure math, philosophy, and maybe even theology. I really hope this explainer sparked your curiosity and helped you see the hidden structures of our world just a little bit clearer today. Keep questioning, keep learning, and I'll see you in the next one.